Welcome to part 6 of differential equations, and this presentation is about systems of differential equations, and there's some practical applications involved here. But I've got this question for you over here. Do you realise that you've already seen some systems of differential equations? That is, a pair or more of differential equations. And here they are here, way back when we were looking at rotational motion around a circle and varying the radius of the motion on that line, the starting point, the angular velocity, and putting them all together at the end. Okay, so do you remember that? And we were generating pairs of differential equations to describe the rate of change of the x coordinate, the y coordinate in that motion. And so what we're going to do now is go on with that. And here's some over here. Here's a pair that look a bit different from what we've just had. This is an interesting pair of differential equations. And then a practical application in a capacitor inductance circuit there, used for generating radio signals. So we're getting into some interesting stuff here and some useful stuff. So let's come on down and start the process. And I want to start with that inductance capacitance circuit. And it's used for producing radio signals. And it's a combination of two interacting elements. First of all, a coil, and you've got a current I flowing through it. And it doesn't matter if you're not into physics. We're going to just do the analysis of the mathematics. So we won't be asking you about currents and voltages as such. And so when it flows through a coil, a voltage is induced. Okay, due to the changing magnetic field there. Okay, the voltage induces against the flow, and proportional to the rate of change of the current. There we have our differential equation. So the voltage induced is in the opposite direction to the rate of change of the current. And that is called the inductance of the coil, how much voltage is induced there. The negative sign in the equation is because the voltage is opposing the current flow, opposite direction. So, how do you get the initial current? Well, I don't know whether you know much about capacitors, but they store current. And so here, when you close the switch up here in the circuit, that stored current in the capacitor will flow. And that produces the, the current in the circuit and your inductance. So here, the current produced is proportional, here's another rate of change, so that's another differential equation, to the rate of change of voltage across the capacitor. Okay, so the current is proportional to the rate of change of voltage across the capacitor. So here, the C constant there of proportionality is called the capacitance. It's a property of the size and nature of the capacitor. So that's enough physics. What we're going to do is see if we can use that pair of differential equations. So at time 0, the capacitor is fully charged and the switch is turned on. The capacitor discharges, and so as it does so, a current flows through the circuit. The current increases as the charge held by the capacitor falls away to 0. Okay, so it flows to a maximum. Change in the current causes the coil to produce more current. And the current continues to flow until the capacitor becomes charged in the opposite direction to what it was initially. The capacitor then discharges again in the opposite direction till we get back to the original situation. Backwards and forwards, backwards and forwards. Hey, do you know a mathematical function that follows that sort of pattern? Okay, the process is oscillatory, oscillating. So we expect, yes, a sine curve. Sines and cosine curves behave like that, growing in one direction and then the opposite direction. So it's no surprise if they tell us that they are the solutions to those differential equations. Okay, and they look pretty much similar to what we were doing with motion around a circle. Pretty similar there. We've got a number, R, out the front if you like, similar, and IP is the maximum current produced in the circuit. So that's going to be a constant for a given circuit. And sine and cos, and then an angle, here and something in front of the angle. So can you see the similarities? And what we're going to do now is see if we can do some maths on these two functions. Don't get frightened by the pronumerals. Pronumerals, although there's a lot of them here, just stand for numbers. Okay, and they describe some properties of the circuit and the properties of the coil and the capacitor. So they just sit there. Don't worry too much about them. Okay, let's come down and see what we can do. So screen clippings here are from Hayes and Harris Publications. So you might have a look at their book there. Okay, so there are our two potential solutions to our empirical or observed rates of change, our two differential equations. Excuse me. Okay, so your job here, show that they satisfy it. So you're not solving these, you're showing that when you differentiate there, get the derivative, that you can show that the two derivatives are in that pattern. Now this is going to involve some fairly complicated algebra, not derivatives. The derivatives are fairly easy, but you're going to have a lot of L's and C's and roots in there. So it may be quite difficult to rearrange the derivatives to express them in that form. So see how you go. Okay, check the initial condition, show that V0 is that. This is all rearrangements now, once you sub in the initial condition. Okay, so then the period of oscillations is going backwards and forwards. Well, we know to find the period of a sine or cosine function, don't we? So that's a hint there. And the frequency down here, and how many oscillations are there in 2 pi seconds. So really this is saying you don't actually have to know about the radio signal and the physics of the circuit. These are properties of the functions, aren't they? Properties of the sine and cosine functions. Well, I'd rather put x there. Sine x and cos x. We're not really using theta as an angle here in this situation. It's modelling with x in radians. Okay, well, see what you think. Have a go, and as you do, go forward and look at the solutions down below. I'll show you those now. Okay, so there's question 1 and 2, 3 also. We'll go down to 4 in a minute. A lot of rearrangement here. As I said to you, it's hard to do the rearrangement, the algebra of it. Okay, let's look at question 4 and 5. Right, let's go on to another practical application. That was an interesting physics one. Are you into chemistry at all? Here we go, we've got a chemical one here. So this process of sulfur dioxide combining with oxygen and giving sulfur trioxide is an important reaction in something called the contact process in the production of sulfuric acid. Okay, so these are real life situations that can be analysed as a budding young mathematician. Okay, so we've got two differential equations, a bit more complicated looking here. And this is the rate of change of the dioxide, D for dioxide, and the rate of change of the trioxide. And there's an equilibrium process here, going backwards and forwards, backwards and forwards. Hey, I reckon that might be an interesting type of situation. So here we've got a rate of change of one that involves how much of each there are, and the rate of change of the other one involving how much of each of them there is, sorry. Okay, so, and here they've shown us potential solutions for the amount of dioxide and trioxide present at any time t, because it's an equilibrium process going backwards and forwards. Okay, now it's not important, absolutely, that you understand the chemistry of this. What we're going to do is to play with these equations and show that these are the solution to these by differentiation, and so on. So, I want you to have a go at this question now, question 1 and 2. Here it is as usual. If it's to show that they satisfy two differential equations, all you have to do is find the derivative, rearrange them and make sure they fit that pattern. That's what we're doing. So I want you to spend a bit of time on this question because it is a practical one. And in exams and tests, people like to see both you're doing a simpler algebra and then transferring it to a practical problem, because that makes it all useful and worthwhile, doesn't it? Okay, so pause the presentation and have a go, and I'll show you the answers now. Okay, question 1, A and B. Again, when you're looking at a practical problem, it's quite likely that there's going to be messy expressions, because it's a complicated situation, a practical situation. It's not going to have just nice whole numbers and stuff. Okay, come down and look at part C. C, D and F, I've got all of question 1 on there now. Okay, very interesting, particularly if you're into chemistry. Okay, go down to question 2. Here we are. So I think the biggest challenge in this area of work is to stick to your guns and be able to apply your basic skills to complicated looking expressions and be able to do some fairly complicated algebraic rearrangements. All right, let's move on and have a look at going back to our rotational motion. And we want to look at this set of differential equations and how they developed coming through here. Okay, how they developed. All right, so this is a revision. This is something that we did back earlier in an earlier presentation. We're going to do it from a differential equation approach this time and just see what's going on there. So let's go down and have a look at the first one there. So just, okay, here's the first one. Consider the set of differential equations of that form. These equations describe the rotation motion of a point in an anti-clockwise direction about the origin. The speed of the object is given by the square root of x component of the velocity squared plus y component of the velocity squared. And the velocity in any instance is that, as the direction of that vector. Okay, so we had a look at that before. Now, show that these are the solutions or satisfy the differential equation shown above. Use the software to view this motion. I'm not going to do that here. What do you notice about the motion of the object? What's the speed of the object? What I want you to do is to pause the presentation, and you can use the disc that comes with the textbook and view it if you like, or just do it mathematically. And each of these questions that are coming up now, I'm going to pause it. You can have a go, and then I'm going to show you the answer. Okay, so pause it and have a go. Here are the answers now. Now, first of all, if we've got to show this is a solution, we're going to get dx by dt. Dx by dt is neg sine t, and therefore you could say that's x prime equals neg sine t, and that equals what? Sine is y, so it's neg y. And you should put as required. And then we'll do dy by dt, excuse me, is cos t, and that implies y prime equals cos t, which equals x. Again, as required. So that is showing that those two equations do satisfy the initial pair. Okay, what do you notice about the motion of the object? And what is the speed of the object? Okay, well, what do you notice about the motion of the object? One could say here that it's uniform. Get rid of that. Uniform motion around the circle. The angular velocity will come up to in a minute. What's the speed of the object? The speed of the object, well, you can't measure it without seeing it there, but the speed is constant. It's actually equal to 1 radian per second, because if we had a look at the speed is the square root of what? We've got x prime squared plus y prime squared, which is sine squared t plus cos squared t. So it's 1 radian per second, or time unit. Okay, so remember this stuff. We did this before. Okay, come down to the next question in this analysis of the simple one. Okay, show that x equals r cos t and y equals r sin t satisfy the differential equation, or the set of differential equations above. Use the software to view the motion. What's the speed of the object? What effect does the coefficient r have on the motion of the object? Okay, pause the presentation and have a go. Let's have a look now. Dx by dt is r neg r sin t. Derivative of cos is neg sin, and that therefore implies that x prime equals neg r sin t, which is neg y again, because y is r sin t. And dy by dt will be, excuse me, r cos t, which implies y prime is just equal to x, again as required. So you're showing that those two x and y expressions do satisfy the pair of differential equations. What's the speed of the object? The speed is again the square root of x prime squared, x prime t squared, plus y prime t squared. And what is that? Well, this time it's the square root of r squared sine squared t plus r squared cos squared t. And so that's the square root of r out the front, and root of sine squared plus cos squared is 1. So it's now r radians per second. Okay, so the speed out on the end of that radius is greater. Okay, because you're further out. Remember, I think I used in an earlier presentation the idea of a person out on a whip in roller skating or ice skating. What effect does the coefficient r have on the motion of the object? Well, it's going to speed up the point on the circumference of the circle, and of course it's going to be out further. That's what the r is. It's going to be on a circle of a larger radius. Do you get that? Do you remember this stuff? Okay, let's go now. We've got a few to do. So next variation is, do you remember what happened if we stuck that in there? Okay, show that it satisfies a pair of differential equations. Use the software. What effect does factor phi have on the motion of the object? Okay, pause it and try to answer the question. Here we go. Dx by dt equals, derivative of this is neg sine t plus phi. So that implies x prime t equals neg sine t plus phi is neg y again, as required. Dy by dt is derivative of cos, sine is cos of t plus phi, which implies y prime t, there, y prime t is equal to x, again as required. That phi has not changed the relationship. And what effect does the factor phi have on the motion? Well, if you sub t is naught in there, phi is going to give you the starting point. And so the starting point has changed. Starting point is phi further around the circle. Just remembering what we're doing here. So we'll usually be starting here at this point, where it would be, excuse me, cos of t plus phi, sine of t plus phi, and if phi is naught, not anything there at all, it will start there, and if phi is a number, it will start further out there. Do you remember that stuff? Okay, that's the effect. We're building this all together for a purpose. You'll see it in the last one. Okay, so part 4. Show that this, putting them all together now, satisfies a pair of differential equations. What are the coordinates of the starting point? Okay, well, let's do it again. Dx by dt will be minus r sine t plus phi, because the derivative of cos is neg sine, so that implies x prime t equals neg r sine t plus I, which is neg y. As before, dy by dt will be equal to r cos t plus psi, which implies y prime is equal to x. Again, as required. Just noticing that when we differentiate this with respect to time, the derivative is the coefficient of t here. Psi is not a function in time, so it doesn't contribute to the derivative. Coordinates of the starting point. So the starting point is at t equals 0, and the point is r cos t 0 plus psi r sine 0 plus psi. Okay, which equals r cos psi r sine psi. So just keep in mind what we did last time, just up there, was we said now that point's going to be the starting point. R cos psi r sine psi. Okay, and this is psi. So you're getting the idea. We've got to build this up. All right, let's move on and do the final little bit of analysis on this basic one. Write down a solution set to the set of differential equations given that the object begins at this point here. So here now what we need to do excuse me, is to say, well, our solution is x equals r cos, what is it, t plus psi, and y equals r sine t plus psi. I'm going to do the first one. You can have a look at the other ones then. So first of all, let's have a little look at what this is looking at like here. So this is x and y. We're starting at 0 for x, neg 0.5, so somewhere down here. 0, neg 0.5. So the radius of the motion there is going to be 0.5, that's a positive. And the angle will be, what, neg pi on 2. Psi would be neg pi on 2. You could work it that way. Or what you have to do with this one up here, I'm going to leave you to have a go at this yourself, is to say, well, if you look at these equations, you can say that if x is 0, 0 equals 0.5 cos of t plus psi, and neg 0.5 equals 0.5 sine of t plus psi. And so if you worked out the tan of t plus psi, the tan of t plus psi equals this one over this one would be undefined. And here, if t is 0, at t equals 0, the tan of psi would be undefined. Okay, so what would the angle be? The angle would be, well, you could say pi on 2, 3 pi on 2, or you could call that neg pi on 2 as I have there. So you can check back with the starting point. So the solution set here is x equals r cos t take pi on 2, y equals r sine t take pi on 2. So there's a unique solution for that case there. All right, getting the idea? Come down, let's finish it off. Okay, if the angular velocity of motion is the angle in radians through which the object turns in 1 second, what's the angular velocity of this motion? Well, let's have a look now. X equals r cos t plus psi, y equals r sine t plus psi. So the angle here, the angle in radians through which the object turns in 1 second, the angle is t plus psi. So the angular velocity, omega, is the derivative of t plus psi with respect to t, which is, this does not contribute, it's not a function in time. Derivative of t with respect to t is 1. So it's 1 radian per second. Okay, that idea, that's where we started. And we're going to build on that rapidly now. Okay, let's have a look at the next set. Okay, so the next set was where we had omega in front. That's from the original table up at the top of this presentation. I want you to pause the presentation, have a go at this first one, using the software if you like to view the motion, get a picture of what's going on, and then I'll show you the answer. Right, so I'm going to give you the answer now. So x equals cos omega t, dx by dt will equal derivative of cos is neg sine, but you must multiply by the derivative of this. So it's neg omega sine omega t, and dy by dt is going to be derivative of this. Derivative of sine is cos, but you must multiply by the derivative of the omega t now. That's got a factor in there. Okay, so we've got that. And so this implies x prime of t is equal to minus omega y, and y prime of t is omega by x. As required, we're showing that on differentiation, those two functions do satisfy the pair of differential equations. Okay, so yes, we've done the first part. Okay, what do you notice about the motion of the object? What is the speed of the object? What's the angular velocity of the object? Well, the motion of the object is still in a circular path. Okay, what is the speed of the object? The speed of the object, well, let's have a look at speed. Speed is again the square root of neg omega y, that's x prime squared, plus y prime squared. And so that equals the square root of omega squared y squared plus omega squared x squared, which is omega by square root of x squared plus y squared. And if you look at x squared plus y squared, of course, that's sine squared omega t plus cos squared, which is 1. So our speed's going to be omega, units, basic units, centimetres per second, if you like. Okay, and the idea there, of course, is going to come up in a minute. What is the angular velocity of the object? The angular velocity is omega, which is, that's a symbol for it, which is just verified as such, the rate of change of the angle with time, which is omega. So maybe I'll put that differently. I'll put the angular velocity is the rate of change of the angle with respect to time, which is omega radians per second. Okay, so that's the idea there. All right, let's come down and have a look at the next bit on this type here. So show that x, now we're putting r in front. We're building it up again, just revising what we did in earlier presentations. Show it satisfies differential equation. Okay, dx by dt, r out the front, and the derivative of cos is neg sine, multiplied by the derivative of that, so it's neg omega sine omega t, dy by dt is again r, derivative of, we better put a bracket around that, r times cos omega t times the omega, so that should be in front. And so this equals what? R by neg y. So this is neg, hang on, better just put that out there. I'll put this in a different package here. Omega r, so I'll put this like this, neg r omega sine omega t, which is r sine omega t. So this is neg w or omega by y, and this one is, putting it out the front, r cos omega t times omega, which is omega x. So that's what we wanted to do this time. We've got a differential equation with the omega in front now. So let's have a look. What is the speed of the object? And here the same thing again. Let's put it down here. The speed is the square root of the x component squared plus the y component squared. So it hasn't changed. What effect does the coefficient of r have on the motion? What is the angular velocity? Oops, hang on, I think I've just messed up speed here. Let's just change the speed here, because what we are looking at is explaining that a bit better. We've got r here and we've got our angle, and what we're going to do is be talking about the motion around the circle. So we want to just make sure the velocity of this point, so you understand this, is x prime equals neg omega y, y prime equals omega x. Okay, so the idea here is that the r is going to be longer. We're going to increase the speed of that, and if we looked at that in this context, then it would be changing. Okay, so it's going to have a effect on the velocity, because when we have our r here, it's going to affect the r x squared plus y squared. The root of x squared plus y squared is going to be have that r in front now. So the speed will change. The speed will be, I left out the r from the previous one. If we do it again here, we will have omega outside of x squared plus y squared, which is omega by x squared plus y squared is r squared by 1. So it's r omega. Okay, so nearly missed that one out there. What is the angular velocity of the object? The angular velocity is the rate of change of the angle. The angular velocity is the rate of change of the angle involved there, so it's still omega. So omega is still the angular velocity. Get the idea? All right, just be careful, don't go so quickly here. All right, let's have a look at that one. Can you have part 3? Show that x is cos that and y is sine that, satisfy differential equations, use the software, etc. Okay, so pause it and have a go. I'll go through it now. So dx by dt is derivative of cos is neg sine omega t plus phi, multiplying by the derivative of this with respect to time, it's just omega, because the phi is a constant with respect to time. Dy by dt, derivative of sine is cos omega t plus phi, derivative of this with respect to time is omega again. So this is neg omega by y, and this is omega by x as required. It's getting a bit repetitive, but the idea is to get these skills up. What effect does the factor phi have on the motion of the object? Phi affects the starting point. Okay, phi further around, it affects the starting point. What is the angular velocity of the object? Let's just check it again. Angular velocity is the rate of change of the angle with respect to time, and so it's still omega, because this is constant with respect to time. Okay, how are you doing? Remembering this stuff? I hope so. Question 4, have a look, show that that and that satisfy differential equations above. We're putting them all together now. All together. Okay, so let's do it. Getting a bit sick of this. Dx by dt is, okay, r's out the front, derivative of cos is neg sine omega t plus phi times the derivative of this thing in here, which is omega. So we can put it as, this is omega times neg r sine omega t plus phi, which is omega neg omega by y. We should really put that out the front, I suppose. Dy by dt, differentiating this one, is r times derivative of sine is cos omega t plus phi times omega. Putting that out the front, it's omega by r cos omega t plus phi, which is omega x as required there. differentiating them to show that they satisfy the pair of differential equations. What are the coordinates of the starting point for the motion? Well, at t equals 0, we can say x equals r cos 0 plus phi, y equals r sine of 0 plus phi. So that equals r cos phi and r sine phi. So again, it's just saying, going to start phi up here. This is now r, just as before. And this is the point r cos phi, r sine phi. Hope you're up with all of that. All right, how are you going? Getting tired? It's getting a bit repetitive, this stuff. Okay, we've just got to be careful. Okay, question 5. I'm going to do the first one and then leave you to do these others, particularly look at this one. Okay, so write down the solution set, the set of differential equations, x prime equals neg omega y prime is neg omega x. So here we are. The solutions that we've just looked at are this. Okay, that one and this one. We said satisfies those differential equations, so we can jump right in there. You might like to get r from, as we did before, a diagram down here at neg 0.5, 0, neg 0.5. And so you can get, if you like, the r is 0.5, the radius arm there, and phi is neg pi on 2 again. Or you can use the idea of tan. So in this one over here, we're going to have to use the idea of tan. Sorry about the little glitch there, but let's go back again and have a look. And we're saying here that with our position of our point here at 0, neg 0.5, we can say that the radial arm has a length of 0.5, and here also that phi will be, when it's 0, this will be the starting position down here, will be neg pi on 2. So you could use tan for this one over here. You might want to divide them out and have a look at tan of phi as the y value over the x value at that starting point. Okay, to get your expression there. So the solution set is x equals 0.5 cos omega t take pi on 2, or plus 3 pi on 2 if you like, and y equals z 0.5 sine of omega t take pi on 2. Okay, so that's the solution set to those. Let's have a look at the new one, the one that is interesting now. So come on down. Oh no, here we are, we haven't done this one yet. So the velocity vector is always perpendicular to the position vector. So the velocity vector is equal to x prime t, y prime t, and the position vector, call it the position vector, is equal to, now, our position vector is just xy. We might like to write this one differently though. We said this is neg omega y and this is omega x. So here let's look at the dot product. V dot the position vector is neg omega y omega x dot xy. So this becomes neg omega xy plus omega xy equals 0. Therefore, V is perpendicular to P. Okay, for all x and y there. So that's as required. So we can use the dot product to show that perpendicular. Okay, so that's an important little proof there. You could do it with sines and coses if you wanted to. Now let's look at the new stuff. New stuff is this business here, where we've got a neg alpha y and a beta x. So that is different. We've always had the same value in there, omega. So that's a different situation. So I want you to pause the presentation and have a look at these questions here. Alright, so there's a couple of ways of doing this. You can actually start those, and I'll scroll down for the rest of the questions down here. And the last couple. But what I'm going to do is exactly what we've been doing. I'm going to take one at a time and have a go. So I want you to read all of that and then see what happens now. So let's have a look at what to do. Here's the first one. Use the software to view the motion. And so this time we're told that these are the solutions. They've got different numbers in front. R is different. That's going to have an effect now. Okay, so what do you notice about the motion? The motion is elliptical. Okay, the different values here are going to pull it away from being circular. The angular velocity. Okay, the angular velocity this time is d theta by dt, and d theta by dt will now be dt by dt. It's 1 radian per second. Okay, as before. Is the speed constant? Well, the speed is going to be the square root of. Now, let's have a look at it. X prime t is minus sine t, and y prime t is cos t. Okay, so we've got the squares of those two added. Let's have a look at what happens. So this is minus sine t all squared. And so this is the square root of sine squared t plus, it's messed up, 4 cos squared t. Okay, so we can't actually get rid of that sine squared plus cos squared. So we could say sine squared plus cos squared is 1, so it's 1 plus and 3 cos squared t still left over. So it's not constant because of t still being in there. Okay, it's not constant, it depends on t. So as we go around, the speed varies now. So that's a new one. All coming about because of these two numbers being different. There's no common radius now, common r if you like. Okay, you might have a look at that disk there and see the motion. Okay, so let's have a look at this one. Adjust the values a and b to view motion of objects covered by the equations here with different numbers. So you're going to have a look at different values there. All right, so now what is the angular velocity of the object? The angular velocity is still the rate of change of this. So the angular velocity is still constant at 1 radian per unit time, per second, because the angular velocity is the rate of change of that angle. Okay, let's go down and have a look. Give you your previous knowledge of the effective parameters omega and phi. Predict what will happen if we have those two numbers different, and then we put these in there again. What do you reckon would happen? Well, I reckon it is still going to start at a new point. And is omega still the angular velocity? Let's check it. The rate of change of the angle with respect to time. Yes, this is constant with respect to time. So it's still omega radians per second. So it's still the angular velocity. So let's have a look at the next variation. So here, what we're going to do is try and look at a solution here. So what we're going to do is say, if they are the solutions, then we want to show that omega A equals alpha B and omega B equals beta A. Oh, let's do some work here. And remember, the equations that they're the solution for are x prime equals neg alpha y and y prime equals beta x. Okay, well, we've got different numbers in front there now. Okay, so here, let's look at the derivative. X prime of t is neg A omega sine omega t plus phi. Okay, and so that we could call neg A omega times 1 on beta y. Okay, from up above there. And that implies now that neg alpha equals neg A omega times 1 on B. Okay, Sorry, I put beta there and I meant B there. Okay, so we're pinching bits from both of these now. And so what we can say there is alpha equals A. Oh, sorry about that. I'll just stop that again now. Sorry about that little glitch. Let's go back and do it again here. So alpha equals A omega times 1 on B. And that implies that B times alpha equals A omega. So that's one thing that we're asked to show as required. And the other one is, let's have a look at y prime. So y prime t equals B omega cos omega t plus phi, getting the derivative of that one. And that's going to be B omega 1 on A times x, if you're thinking about working the x in there. And that is beta here, so we can then say that beta equals B omega 1 on A. We're using this business up here. Alright, so if we rearrange that, we've got beta times A equals B times omega. Again, as required. A little bit of funny algebra going on there, and you've got to be able to do this in tests and exams, manipulating the derivatives around and getting useful expressions. Okay, so because we're going to use this in a minute to solve the equation and get from this form up to the solutions. So have a look at that and see what you think. Alright, so let's go down to the next one. Multiply the equations in 4 to get those results now. Obtain a ratio for A over B in terms of alpha and beta, and what's the physical meaning of that ratio. Alright, so let's use what we've got. So we've got omega A equals B times alpha. So let's get A out of that. A is B times alpha on omega. And the other one is, if we sub that into, so you've got to be a little bit tricky here, sub that into the other one, omega B equals beta A, then we've got omega B equals beta times B alpha on omega. And then we can rearrange that. Okay, so here omega squared is going to be equal alpha times B, dividing both sides through by B there, beta. So we've divided by, divided by B. This will be a beta here. This will still be left. Okay, we've divided both sides by that one. So omega is going to be the square root of alpha beta there. Okay, now if we use that, that's using the equations multiplied together, then let's consider A over B now. If you look at A over B, we've got them in reasonable terms. That's B alpha over omega all over B. Okay, and we can therefore say this is cancel this alpha over omega, the b's will cancel, and this is then alpha over the root of alpha beta from here, and therefore that's the root of alpha, that'll go into that root alpha times over root beta, or the root of alpha on beta. Oh, yeah, so that's our A over B expression. So this algebra is quite complicated, and you could be asked to do this in tests and exams, manipulating pairs of differential equations and coefficients that you haven't seen before. All right, so let's go down to the next bit, have a go at this one, and see what you think. All right, so what is the Oh, hang on, I haven't finished this, have I? I don't think I said what was the meaning, what's the physical meaning of this ratio? Okay, and that's the ratio of the maximum x displacement, max x displacement is A, divided by the maximum y displacement, or the ratios of the axes of the ellipse. Okay, this as to this, the ratio of the lengths of these axes there. Okay, so think about that when if you've seen the motion using the disc. Okay, so it's elliptical. Excuse me. Now, let's have a look by setting out t equals 0. We know the starting point must be this, AB. Show that tan of phi is B on alpha root alpha on B. Okay, so let's write out the equations now. X of t is A cos omega t plus phi, and y of t is B sine omega t plus phi. Excuse me. At t is 0, though, we've got the point B is the point A cos, now 0 plus phi, or just phi, and B sine phi. Okay, so we've just shown that. So here, that's the point AB is equal to this. Okay, so can we now, can we now find values here? A is A cos phi, and B, little b, is, let's just get rid of that, little b, can't get rid of that, little b is B sine phi. So we've got those two results. So now, what can we say? A over A is cos of phi, and B over B is sine of phi. So, just come down a little bit, run out of room here. So what we can say therefore, the tan of phi is sine over cos, which is B over B over A, got to be careful here, which is B over A times A over B, dividing by that fraction you invert and multiply. So this is B over A times the root of alpha over beta as required. Okay, so this is from part 5. Okay, so we finally got there. So you've got to be a little bit manipulative here and do the algebra. That's a problem of it, I suppose, for most people. Let's have a look then at how we can use this. In 7, let's do the first one. I'll leave you to do the others there. So what we're going to say in this case is we know the solution is, from what we've done, these things, and we've got to go and find all the values we need here using what we've established, B sine omega t plus phi. Now, where do we start? Well, we know omega is the square root of alpha times beta, and we know that A over B is the root of alpha on beta. Okay, so can we work out omega? Alpha is, in this case, what is it up here? Neg 1, and beta is 2. So, no, alpha is just 1. It's not the 9. It's neg alpha y, isn't it? So it's just 1 by 2, which is root 2. And A over B would be equal to 1 on root 2. Okay, come down, need a little bit more room here. Now, at t equals 0, let's use that. X equals A cos phi, and y equals B sine of phi. So we can say this is equal to root 2, and this is equal to 0. So they are the two initial conditions there. So what we can say therefore is B sine phi over A cos phi is equal to 0 there, right? That one, yeah, over that one, that checks. So A cos phi is equal to root 2, implies A cos of naught is root 2. So therefore A is root 2. Running out of a bit of room here, so just come down a little bit. But then come over here, but here A over B is 1 on root 2, so that's root 2 on B, so that implies B is 2. Okay, multiplying across if you like. So the solution, a lot of work this, is x of t equals root 2 cos root 2t, and y of t is 2 sine root 2t. But the idea now is to go back and try to do that sort of thing, excuse me, that sort of thing as part of the other solutions up there, B, C and D, just checking that out. All right, so what are we up to now? What we're going to try and do is to summarise with some formulae there. If we do have different values in our differential equations, neg alpha y and beta x, then we can say that these are the forms of the solution. So we're not solving these directly like we did with the logistic equation. We're checking out this form for the solutions, and we can say omega in the solution is the root of the coefficients there, and then the ratio of A over B and the cos and sine values at the 0 position give you the tan of the angle. So it's a lot of algebraic manipulation. All right, come down and have a look at it in action from Hayes here. So we've got neg 3y and 2x. We're going to say that the form of the solutions is, as we said before, A cos omega t plus psi and B sine omega t plus psi. And we've got these initial conditions. So work out omega using our relationships, then subbing in. So we'll get tan theta is undefined. We'll get pi on 2 therefore. And then we can say B sine phi is 2 and B is 2, and work out A from the relationship of A over B being root 3 on root 2. And then put our solutions together, A and B and our omega there and our phi. So it's all juggling the numbers, isn't it, the coefficients. And you could check your solution. Always, well, you probably wouldn't have time in tests to check your solution, and also recheck the initial conditions. Check that when you put t as naught in here, it works. All right, have a look at the last set of exercises here, 9A3. So it's the same sort of stuff, going through the relationships, and here you need to propose the form of the solution. And this will generally be given to you in tests and exams for pairs of differential equations. You're not expected to try and solve those. You are proposing that the form of the solution is A cos omega t plus phi, and that y is B sine omega t plus phi for anything of this form neg alpha y and beta x. Okay, so they happen to be the same there, don't they? So think about that one. Okay, and here's an interesting one, probably a possibility for an exam. Here we're asked to do the same sort of things. Here, look at the form of these differential equations and transfer it across to a practical problem. All right, bit of a headache there. Well, I want you to pause the presentation and have a go. I'm going to show you the solutions now. Okay, so there's question 1. Check it all out, it's the same stuff there. And then question 2. The rest of 3. So we'll look at question 4. And question 5. Alright, so fairly challenging systems of differential equations. So might have to go back over it a couple of times. For me now, it's cheers for now.